Hey you guys, here's your first installment for thermochemistry. Now thermochemistry, it can be a little challenging because there's a lot going on and a lot of analysis that's going to be done for processes that exchange energy. And the energy, these are chemical processes, and the energy that's being exchanged in our situation is going to be heat. And you can see heat being showing up in this explosion. This is the Hindenburg, which was a large, they called it a dirigible or a blimp that was filled with helium or hydrogen. And then this one ended up catching fire and crashing and burning. So, of course, thermochemistry is involved there. Heat is being given off. And what's interesting about this guy is there's also a change in volume. The change in volume started that it had a very large volume of hydrogen gas inside here. And when it was all done and on the ground, it had zero as far as volume was concerned, volume of hydrogen gas. So that's why this picture is included in your chapter on thermochemistry. There's a picture over here that's included in your chapter. It's in one of the chemistries in action that talks about snowmaking. And snowmaking, this little apparatus here is taking advantage of the first law of thermodynamics. And we'll talk about that in a couple slides later. So as far as energy and just kind of tracking what energy is, there's some different types of energy. The first type that we're going to look at here, let's first define energy. Energy is the capacity to do work. If you have energy, you can do work. Now, what types of energy can we be looking at? We can look at radiant, which comes from the sun and is Earth's primary energy source. That makes sense. The sun is beating on the Earth all the time. Just depends on which side is towards the sun, is how hot it is, or where it's at in its orbit, the Earth's orbit. Chemical work. Now, chemical work you can kind of think about as a directed energy change resulting from a process. A lot of times we can think of this as explosions. And an explosion is something that is definitely a directed energy change, and it results in a change in volume of gases as well as heat being given off during that process. So chemical work is usually a result of bond breaking or making. Thermal energy is the energy associated with random motion of atoms and molecules. So when you have a sample of air, and if that air is hot, they're moving very fast. If the air is cold, it will sink down to the bottom of the container because it's moving slower. Chemical energy, then, so we had chemical work, which is a directed energy change, like an explosion, and that process can be just a chemical change and from chemical energy, and it's stored within the chemical bonds. So when we think about a type of explosive like nitroglycerin or things like that, bonds are broken, and when those bonds are broken, then you have products, and those product molecules have bonds also. But we know that when we have reactants over here, when those bonds are broken over here and remade over here, energy goes in to break bonds, but when bonds are made, energy is given out. So if more comes out than is put in, that's an exothermic process. If more is put in than got out, then that's an endothermic process. So potential energy then is the energy available by virtue of an object's position. We don't really think about that too much in chemistry. We think of chemical potential energy in the form of bonds. So you can think about it that way, but not necessarily like a skydiver. So in this picture from your textbook, it's showing a dam, and there's higher potential energy on this side of the dam. And as that water falls through a certain distance, that energy is converted into kinetic energy. So your fun sheet on question number 1, it's asking you through a little narrative to identify these types of energy. So as far as chemical reactions are concerned, what we're looking for is the heat transfer. So heat is the transfer of that thermal energy between two bodies that are at different temperatures. So what is temperature is a measure of the thermal energy, but they're not equal to each other. So I can measure the temperature of a block of metal, and that temperature of that block of metal, if it's higher, say it's hot, and the temperature on the outside is cold, and you put your hand near here, you will feel that heat radiating off of that hot block of metal. And so that heat is that which moves from an area of high temperature to an area of low temperature. So that's a definition of heat. hear from physics books a lot of times, but it's the transfer of thermal energy. So that means outside this hot block, the molecules were moving slower than they were on the inside of the block. So this is a picture out of your textbook that's showing a thermal view of a house, and you can see that thermal energy is escaping through the windows, but not as much as through the walls. So thermochemistry then is the study of heat change in those chemical reactions. So but before we can move on to chemical reactions, we have to make some definitions here of the system. The system is the specific part of the universe that is of interest. So if this is my bottle and this bottle is a system, if this is a certain type of system that is open, that means heat can get in and out through the walls and mass can get in and out because it's open. So mass and energy can be exchanged in an open system. In a closed system, only energy can be exchanged through the walls. And then in an isolated system, mass or energy cannot be exchanged, and that's like a perfect ideal system. That means that energy, whatever was in here, would stay there forever. So nothing can go in and out. So as far as this heat exchange, we want to go over the terms you may have heard before, exothermic and endothermic. And an exothermic process is a process that gives off heat and transfers thermal energy from the system to the surroundings. So you could say sys to surroundings. That's the direction of heat flow from in an exothermic process. Now, of course, you have to know what your system is. So always just make sure to define that when you're thinking about a problem. So in this example, hydrogen and oxygen are reacting to make water. And when that occurs, energy is given off to the surroundings. This is an exothermic process. This is the process of water in the gaseous state condensing to water in the liquid state. And this is also an exothermic process. So when dew forms overnight, that dew came from the air, that was water in the air, and then it condensed down onto the plant in the form of a liquid. And when that happens, energy is given off in the form of heat. So you'll get a little bit of a heat spike when that occurs when you reach the dew point. Endothermic is a process in which heat has to be supplied to the system from the surroundings. So in this example, this is this mercury 2 oxide being heated, and mercury liquid and oxygen gas are given off. But in order for this process to occur, energy has to be input. And usually this is just in the form of a flame on a test tube of mercury oxide. So when you write it, an endothermic, the energy term goes on the left. So this is melting of ice, solid to liquid. And when that occurs, energy has to be absorbed. So you'll notice outside in the wintertime, if there's a lot of snow around, it just stays cold. And that's because even the sun's out. And that's because a lot of the radiant energy is going to melt all the ice that's around sitting on the ground. So as far as what it looks like schematically, your book uses schematics of an exothermic process that the reactants are in a higher energy value than the products. So, or in an endothermic, the reactants are in a lower energy value than the products. So a lot of times you'll see little graphs that look like this. In an endothermic system gains energy, and then the products are at a higher energy than the reactants. And this would be energy over here over time. And then that would be the opposite for an exothermic reaction. You have reactants, and then the products are at a lower energy state than the reactants. And this difference that you see here, here's energy over here. This difference that you see from this point to this point, this is the amount of energy that's given off when this process occurs, minus the, see this is called the activation energy. And the activation energy is required to get it going. And actually I did that backwards. Now this activation energy is higher. This is the activation energy that was required to get this reaction started. And that should be called EA, not AE. It's activation energy. But then still this difference between reactants and products, that's the amount of energy that was absorbed in that process. Now, sometimes that activation energy is higher than what you get out. So this is showing that you put in more than you got out. And that's why it's an endothermic reaction. This one you got out, look at this graph over on the left, you got out more than you put in. You had to put in a little bit of activation, but you got out a lot more. And that this little value here, this is the amount of energy that you would gain from this product. So thermodynamics then is the study of this interconversion of heat and energy. So what's important about state functions, and we're going to be talking about a few different types of measurements, is their properties that are determined by the state of the system, regardless of how that can is because if you can measure, just like I was drawing those graphs, if I can measure the initial state, like this is initial here and this is final, I don't really care how I got there. And since I don't care how I got there, I can just measure the initial and the final, then I can know how it's changing. That's what a state function is. So energy is a state function. So potential energy, and your book uses this picture that both hikers start at the bottom of the mountain. The red hiker looks like it went a different path than the blue hiker, but they both ended up at the same spot. So their change in is the same, but it doesn't matter how they got there. So that's why we don't have to know that part for a state function. So energy is a state function. Pressure, volume, and temperature are also state functions. So when you see this in your textbook, this delta E, delta P, delta V, and delta T, doesn't really matter how it got there. It's just the point that it's different. Now your book uses delta U. It uses U for internal energy of a system. Other textbook use an E. So either way, as long as you know what you're doing, it doesn't really matter which letter you use. So as far as thermodynamics then, the first law, like we were talking about that making snow, is that energy can be converted from one form to another, but it cannot be created or destroyed. And why this is important is because that means you can track it. If you know something disappeared, you can look for it where it showed up. So as far as energy is concerned, that when your system and surroundings, they must equal zero, or they're equal and opposite to each other. So if the system loses energy, it must go into the surroundings. If the surroundings loses energy, it must go into the system. So as far as defining the system and surroundings, that's where we get the little gray and fuzzy, because if you know what it is, then it's not gray and fuzzy. So let's try to make sure we define our system. So in this picture, looks like we have a system that is propane. It's a combustion reaction. And during that combustion reaction, there's an exchange of energy. We know heat is given off to the surroundings. So this would be your system, and this would be your surroundings. And that's what defines an exothermic reaction, as that heat is transferred from the system to the surroundings, and the surroundings get hotter. And it's exothermic. So chemical energy lost by combustion is energy gained by the surroundings. So this is chemical energy lost, looks like it's being converted to thermal energy, which is gained by the surroundings. And there are products here. Remember I said earlier that bonds are broken. Bonds are broken when a chemical reaction occurs. And then also bonds are made. So we break bonds, which requires energy, and then bonds are made, which gives off energy. So according to this equation, if this is exothermic, then that means more energy was given off during bond makeage than was taken in during bond breakage. So our little graph would look like this type of thing. So there was more gotten out than was put in. So this first law of thermodynamics, we're talking about what is the first law. It is energy cannot be created or destroyed, just transform from one to the other. So this is written in equation form as a change in energy is equal to this Q, which stands for heat, and W, which stands for work. Now your book uses U, but you can use E, so your book uses delta U here. And that's the change in internal energy of the system. Internal energy, a system is just sitting there, it has energy. And when it changes, that's when you can see something happening. Now, when something is happening, it can be in the form of heat or it can be in the form of work. Now, with explosives, they do both. An explosion explodes, energy is given off in the form of heat, but also gases, so that would be heat in your explosion. But gases are created that expand very quickly out into the surroundings. So if you're a building standing here with your windows and those gases come out, they will knock the building over. So because of this change in volume of the gases. So that's how explosives work. But we're going to analyze this a little further. So Q, again, was heat. That's what I was pointing out a moment ago. W is work done on or by the system. So in our example, our explosive is doing work on the system. If our explosive, on the surroundings. If our explosive is the system and the surroundings is the building, then when it explodes, it does work on the surroundings. So this work is tracked in chemical reactions by a change in volume. If a gas expands against something, it can be against a pressure, and that pressure can be a building or it can be just the atmosphere around it. So if you have an explosive device and it explodes, you will end up with pushing back the atmosphere or knocking over a building, depending upon the proximity of those surroundings to that point of explosion. So as far as trying to figure out this sign convention, a sign convention is there because it tells a story. And what our equation that we're looking at is work and heat. And we know that our delta U is equal to work and heat combined. So when something expands, how I remember this, what we're looking at is a change in internal energy of the system, is an interplay between work and heat. So when something expands, if our system, say for example, our explosive material, our explosive material was just sitting here, and that then when it was initiated, it exploded, and when it exploded, it did work on the surroundings, and itself has now lost energy, and since it gave it to the surroundings, and since it lost energy, if there's an expansion, look down here in the table, that W is negative. Because when we do our equation here of delta U equals Q plus W, if our explosion or our reaction does work on the surroundings, this W becomes negative and makes the energy overall of the internal energy of the system decrease. Vice versa, look up at these little piston examples. If you have a piston like this and it compresses a gas, it has compressed that gas to where then it could bounce back. So when you compress a gas, you know that it now can explode back at you. So you're basically giving it energy. And then it could just pop back again. So compression, you have a positive value to the energy. Expansion, you have a negative value. So sometimes it actually works out, because when you're doing this definition of that W equals minus P delta V, that delta V, remember delta is always final minus initial. So when you do this calculation and your final value is smaller than your initial value, that would be, if your final value is smaller than your initial value, that would be a negative. So then a negative times a negative is a positive, and that was giving it energy. So for the Hindenburg example, remember on the previous slide that I was showing the Hindenburg burning. Let's say this one had this Hindenburg blimp had a volume of 3,000 liters of hydrogen gas. That was its initial volume. Its final volume, say, was 0 because it burned. So your change in volume is negative 3,000 liters. And so a negative times a negative ends up being a positive, and that means that system has more energy than where it started. Now we have to be careful with this type of analysis, because a lot of times it's more like a piston analysis, not this type of analysis, but we can still roughly apply it to that. Now let's talk about Q, which is heat. Heat absorbed by the system from the surroundings means that system gained energy. It is endothermic, and that's why it's positive. It gained energy. If the system gave off heat to the surroundings, it lost energy, and that's why it's negative. And you put a negative here, and your internal energy decreases. So on your fun sheet, I asked you a question about rising bread. When bread rises, it pushes back the atmosphere. If you're making bread and it's a risen bread that you put yeast in there, it will rise. And when it rises, it pushes back the atmosphere, and that must mean that it did work on the atmosphere. Might not have done much, but it did something, because you can't have something rise into the atmosphere without moving the gaseous molecules around it. So try that rising bread question. We're going to look at that here in a little bit. But let's just do a quick example of how to use this work relationship formula. If you have nitrogen gas and expands in volume from 1.6 to 5.4 liters at a constant temperature, what is the work done in joules if the gas expands against a vacuum and against a constant pressure of 3.7 atmospheres? Now remember, W equals minus P delta V, and most of the time we are looking at like a little piston idea here. If we had some nitrogen gas in here, it was at 1.6 liters, and then it expanded to 5.4 liters against a vacuum. Now, if it's against a vacuum, you have to think about, when we do work, how much pressure are we working against? And in a vacuum, the pressure is 0. And when it's 0, there's no work done. It doesn't matter how much you expanded. So does that mean that that's why the universe is expanding? They say the universe is expanding, and it just continues to expand because it's expanding into nothing, and that's why it's doing no work. And that's why it can even expand that large. You know, I don't know. I've never asked myself that question before. Okay, so that would be 0 joules of work for this example. How about letter B? Letter B, now there's the same change in volume, but now you have an external pressure of 3.7 atmospheres. So let's go back up to our drawing so you can think about a certain amount pushing down. And when that's pushing down, that's a pressure that that nitrogen has to work against. So that's going to go into your calculation. So now you put in your change in volume and you put in your atmospheres that it's working against. And so this is a liter atmosphere. Now I want to point out that a liter atmosphere can be converted to, since this is work, this is an energy, we need an energy unit. And this is not necessarily an energy unit, but there is a way to convert that to an energy unit. And that is that 1 liter atmosphere is 101.3 joules. So remember, when we were talking about our first law of thermodynamics, and where delta U was equal to Q plus W, when you do this calculation and you want to know work, you have to put it into joules, because Q is heat and that ends up being in joules. So we have to make sure that our units match. So this is the conversion for liter atmospheres, a work of a liter atmosphere, which is an expansion of a gas of a certain amount of liters. Convert that into joules using this conversion factor. And there it is. So your answer for this one would be 1,430 joules of work was done to expand of this nitrogen expanding. Notice it's negative. It's negative because the nitrogen did work and itself lost energy. Okay. So as far as being done, work done by the system, we're still kind of looking at the same thing. This is the same idea. This slide is going to give you kind of the same information, that work done by the system is calculated through this relationship, and that if your change in volume is positive, then your work will be negative, and that's because it lost energy. Now, work is not a state function. So as far as, you know, how much work do I do depends on how I do it. So just to make sure that there is no change in work, the only thing you can use is change in volume to figure out the work. So as far as the fun sheet on this section 6.2 was talking about bread. You know, you make bread and there's yeast and then there's sugars in the flour, and then that yeast starts working on those sugars. And then there is some fermentation that goes on, and carbon dioxide is created, which is a gas, and it starts to expand the dough. So as far as thinking about the first law of thermodynamics and work and heat, let's think about our system first. Does this reaction occur in an open, closed, or isolated system? It's not in the oven yet. So when you think about it, you mix up your flour and you got it in a bowl. Now you've made dough and now it's sitting here. Is that open, closed, or isolated of a system? And then when the bread does rise, is it doing work on the system? Or does the bread do work on the surroundings, or is work done on the bread by the surroundings? So remember, the dough is rising, and there is an atmospheric pressure out here. So when you're answering this question, think about that. Let's go on to the fun sheet question number 3. Now that we were thinking about that bread rising, the bread was dough and it was in here and it was rising. Calculate the work done at sea level and in Colorado Springs. So sea level, remember, is 760 millimeters of mercury, is the atmospheric pressure at sea level. And in Colorado Springs, it can hover around 600, and that's because of our altitude. So work, you got to think about, are you going to do more work at sea level or more work in Colorado Springs? So just think about that relationship of W equals minus P delta B and calculate the work and put that in joules using that conversion factor of 101.3 joules per 1 liter atmosphere, 1 liter ATM. So now that's calculating how much work the bread does when it's rising. And this part is now figuring out how is the internal energies of the bread system changing based upon, once you start adding heat to it, because this heat transfer happens in the oven and it's given to the bread. And then we can utilize our delta U equals Q plus W to determine the change in internal energy of the bread system. Because we put in so much heat, there's so much work done either on the system or by the system, and you got to figure out the sign for the work. Is it positive or negative? You have to figure out the sign for the Q. Is it positive or negative? And that depends upon whether energy is given to the system, heat. If heat is given to the system, that's endothermic, and it would be positive. If heat was withdrawn from the system, it would be negative. If work is done on the system, it is positive. If the system does work on the surroundings, it would be negative. So think about that when you do your change in internal energy calculation. So that's it for this first installment. And if you have any questions, please post those to the discussion board or send me an email. Thanks.